We've got space.
All right, we're recording. So we're talking about black holes, right? Yes. And so we're going to talk about the speed of light as measured locally, as measured in force field coordinates, and learn more about the event horizon. So remember last time we were pointing out that if you look at the Schwarzschild metric, which of course is that ds squared was c dt square root of 1 minus r sub s over r squared minus dr over the square root 1 minus r sub s over r squared minus r sine theta d phi squared, minus r d theta squared. They put it in the. Is that the order I normally put it in, or did I switch that around?
No, it seems right.
What's that?
It seems right.
Well, it's right. I just put it in a different order than I normally do. So I guess I'll just put it in the order I normally do, which was to put the r d theta term next to it. So, yeah, that's what I have here. So minus r d theta squared minus r sine theta d phi squared. Here we are using the Schwarzschild radius is 2gm over c squared, so that's what's normally inside the square root, and we are giving it an interpretation, the Schwarzschild radius. Schwarzschild radius is the value that makes the square root 0. So it makes those square roots in the metric equal to 0, and we said that as seen by a faraway clock, then t infinity becomes infinite. Because remember, we said that the time is measured infinitely far away, divided by the time as measured at the location of the clock was, I mean, we've done this, but I figured it's good to remind you of where we were, was 1 over the square root of 1 minus rs over r. And so if the square root goes to 0, t infinity goes to infinity. So you get infinite redshift at r equals rs. If you had something at r equals rs, then as seen from far away, the period of the clock goes to infinity there, and the frequency of the light wave emitted by it would become equal to 0. And so that's one way of understanding the idea of why we call it a black hole, because for something at the event horizon, you would not see any radiation from it because the redshift becomes infinite. It goes to 0 frequency. It goes to infinitely long wavelength. So, any questions about that? Including, I forget what we were doing with that.
Could you say?
Yeah, so this is the period of a, so if I've got, here's the Schwarzschild radius, here's, so this is r equals rs, and sometimes people make these pictures where they kind of label the Schwarzschild radius, but that's really BS because it's not literally distance from the center. So here's the surface for which the radial coordinate is equal to the Schwarzschild radius, which means that its area is 4 pi times the Schwarzschild radius squared. And if we had something that, if we had a clock at that location that was trying to send the light wave out to a clock very, very far away, if we look at the time dilation formula, the time between ticks measured at infinity divided by the time between ticks as measured at the clock itself, that's always given by this formula right here for whatever radius that you're at. And if we plug in the Schwarzschild radius, this says 1 divided by 1 minus 1, or square root of 1 minus 1, or in other words, it becomes infinity. So the period of this clock as seen by a clock very, very far away, becomes infinite. It takes forever between ticks, which means essentially that, from the outside, in this image, you see the clock as having stopped once it gets to the Schwarzschild radius. The time dilation becomes infinite. The other piece of that is remember that the other side of the coin of gravitational time dilation is gravitational redshift. If you think of a wave crest as being emitted with each tick of the clock, there's an infinite amount of time between wave crests as seen from far away. In other words, the wavelength has been redshifted to infinity. The energies of the photons have gone to zero in this limit. So you're not going to see any light from the Schwarzschild radius because of the fact that the redshift becomes infinitely large there as well. So again, that's a way of understanding why we call black holes black. You can't get any radiation from the Schwarzschild radius, or for that matter, from the sun. Okay, does that make sense? Okay, let's look at it another way. Let's look at the speed of a photon as measured in Schwarzschild coordinates. Okay, so a freely falling observer. So you are chilling. You shouldn't be chilling. You're near a black hole, but you're kind of stupid. So you're in this free-falling compartment near the black hole. You have some clocks and meter sticks inside your free-falling compartment. You fire off a laser and you measure the speed of the photon. What do you get from the principle of equivalence? In your freely falling frame, you have eliminated the effects of gravity. And so you get the same results you would if you were just drifting in space, far from any stars and planets. If you're drifting in space, far from any stars and planets, and you measure the speed of light, what do you get? Yeah, you get c, right? The classic 2.99792.458 times 10 to the 8 meters per second. So what do you get in the freely falling frame with your freely falling clocks and meter sticks? What are you going to get for the speed of light? Same thing. You are going to get c. So you're always going to measure c for the speed of light in that freely falling frame. But let's talk about what we call the coordinate speed of light. So first we'll note that a freely falling observer always obtains c when measuring the speed of light. That's just the principle of equivalence. But the coordinate speed of light differs from c. The speed of light as measured, as specified, if you will, not really measured, but because not what somebody would directly measure if they were next to the photon. But if you keep track of the photon's trajectory in Schwarzschild coordinates, and you look at, for a radially traveling photon, what is dr dt, rate of change of the radial coordinate with respect to the Schwarzschild time coordinate t, the faraway time, we will show that that's less than the speed of light, as a matter of fact. The coordinate speed of light differs from c. So let's consider a radially traveling photon. It's moving along a straight line towards or away from the origin in Schwarzschild coordinates. So since it's radially traveling, then what does that tell us about the angular coordinates? How do they vary as the photon moves? How do theta and phi for our radially traveling photon vary as the photon moves? Hint, yeah, kind of a trick question, right? They're not changing. They're moving a straight line away from the origin is one of constant theta and constant phi, because theta and phi just specify direction in space from the origin. So d theta equals d phi equals 0. The only things that are not 0 are dt and dr. We have that ds squared equals 0. It's equal to 0 because remember that photons travel along null geodesics, ones where the proper time elapsed is equal to 0, and ds squared is related to the proper time, right? So ds squared is c squared d tau squared, where d tau is the proper time elapsed on clock carried by the particle, but for photons, the clock doesn't elapse proper time along its world line. So ds squared is equal to 0 is equal to, well, we only need the first two terms here because d theta and d phi are equal to 0 along the world line of the photon. So we get 0 is equal to c dt times, and I'll just go ahead and put in the 2gm over c squared. Square root of 1 minus 2gm over c squared r for the time piece, minus dr over the same square root for the space piece. On the photon's world line, that's the specification, starting along the world, a null world line, and that tells you how dr and dt are related along different points along the photon's world line. If you know dr, you know dt for points along the world line of the photon and vice versa. Zero there because the photon world line is a null geodesic. So now we can just solve for dr divided by dt. Because that's equal to 0, so therefore you pull the dr term over to the other side, and then just divide by dr dt. So dr dt for our photon will be equal to plus or minus c times 1 minus 2gm over c squared r. Because when I move the dr piece over to the left side of the equal sign here, and I divide through by dt, I'm going to take this square root and multiply it by this square root and undo it, so to speak. Okay, does that make sense? Are you happy with that? So we could also put in what the Schwarzschild radius is. So this is plus or minus c times 1 minus rs over r. Why do I say plus or minus c there?
Because I took the square root.
Because I took a square root. Yeah, I took a square root, and the square root could be plus or negative, plus or minus. Physically, plus or minus corresponds to what? The photon could be moving in or out. Yeah, so the plus or minus is reflecting the photon being an outwardly traveling photon or an inwardly traveling photon. Both are certainly allowed. So I've got c plus or minus c times 1 minus some value. And here we are outside the Schwarzschild radius, so whatever r is, it's bigger than rs. So this is less than c. Right? The coordinate speed of light is less than c, because I've multiplied c times something smaller than 1. But then look what happens when we let r approach the source shield radius. It goes to 0. Coordinate speed of light goes to 0. As r approaches the source shield radius, the RDT for our photon approaches 0. Or in other words, as we approach, if we reach the source shield radius, the photon is frozen, so to speak, as reckoned by the Schwarzschild observer. And by the Schwarzschild observer, I mean the contraption of clocks that have been set to run at faraway time, by deliberately setting them fast. And the closer they are to the Schwarzschild radius, the faster they have to be running in order to match what you would see for the rate of clocks far away, ticking if you were at those locations. So the photon is frozen. As reckoned by the Schwarzschild observer. In other words, a photon launched outwards from r equals rs never reaches a greater radial coordinate as measured by faraway clocks. Because remember that dt is faraway time. It's time as measured far away, where space-time is essentially flat. And so this is saying that the photon takes an infinite amount of faraway time for any change in its radial coordinate to happen. In other words, its radial coordinate is staying constant. It's not going anywhere, is what it comes down to. So a photon launched outwards from r equals rs never reaches a greater radial coordinate. And remember that if the faraway observer sees the redshift and time dilation go to infinity, so does everybody outside the Schwarzschild radius. No matter how close you are to it, the time dilation you observe of the Schwarzschild radius relative to you r is infinite. So it never reaches a greater radial coordinate. Light cannot escape from r equals r sub s. So not only do we say the black hole is black because light trying to reach us from the Schwarzschild radius would be infinitely redshifted, it also can be said that a photon launched from there would never go anywhere. It's just frozen in place there, as reckoned by anybody outside the Schwarzschild radius. So no matter how you slice it, light cannot escape from the black hole, because photons, as seen from the outside, cannot move if they're located at the Schwarzschild radius. Since no information can reach the outside world from r equals rs, we call this spherical surface the event horizon. sure you've heard that term before. So in other words, the short shield radius is the radial coordinate of the event horizon.
That's cool.
Questions? Comments, observations? There are no observations. Yes. Good point, yes.
Oh, shit.
Right. So here's a weird thing then. Star collapsing to form a black hole. As the material approaches the event horizon, it slows to a stop and never actually crosses it as seen from the outside. So in other words, now, in a sense it doesn't matter. As seen from the outside, the black hole's going to be black because you're not getting any light from it. But also note that in fact it's a misconception really to think of, as seen from the outside, the star collapses inside of its own short shield radius and becomes a singularity, blah, blah, blah. That never happens as seen from the outside. The material just gets frozen as it approaches the event horizon. So apparently in the Soviet Union, the word for black hole was essentially frozen star, because it never actually gets there, it just stops, basically. So, kind of weird, is what it comes down to.
So from the outside, does anything actually happen? If time basically comes to a standstill, and nothing ever actually reaches it from the outside, can it be said that anything actually happens inside a black hole?
It can, but here's kind of the weird way to look at it. So if you were falling towards the event horizon, you would not feel yourself become frozen. You would in fact fall right through the event horizon. Well, this is assuming there are arguments that you might hit a so-called firewall, that because of quantum mechanical effects, you might get incinerated as you approach the event horizon. If I recall correctly, it's basically you'd be hitting the Hawking radiation or something like that. I forget the details of that. But
RIP.
what's that?
The RIP.
Yes, RIP, right. But without worrying about that, just classical general relativity, you should just be able to fall right through the event horizon. And if you didn't get spaghettified, in other words, if the black hole was large enough that the tidal forces didn't rip you apart before you fell through the event horizon, you wouldn't notice anything special. If your compartment was completely closed off, you wouldn't even know that you'd passed the event horizon and were now inside the black hole. Everything would continue on as normal, as seen by you. But you would start, as you got closer and closer to the singularity, you'd feel more and more tidal effects. And eventually you would be spaghettified. But if the black hole had enough mass, its radius could be big enough that you would not be torn apart before crossing the event horizon. So wait a minute. We're saying that as seen from the outside, you never hit the event horizon. And yet, if you were in the falling compartment, or you were just falling by yourself, you fall right through no problem. The way to interpret that is that the black hole is the events which cannot be consistently mapped onto the outside universe in terms of any kind of simultaneity with them. They sort of happen after all of the future as seen from the outside. They're simply unreachable from the outside. That's another way to think of being inside the event horizon. You're cut off from the rest of the universe. Once you've gone inside the event horizon, in a sense, this is a very sloppy way to put it, but the future has completely happened and it's all gone from the outside. It's taken more than an infinite amount of time, as seen from the outside, for you to get inside there. Those events simply can't, the events that are the black hole, the stuff inside the event horizon, cannot be consistently mapped, if you will, to the rest of the universe, because they happen after time equals infinity on some level. Weird, but that's what it comes down to. there simply is, it doesn't make any sense on some level to say, what's happening inside the black hole right now? Because there's no frame that you can say events inside the black hole are simultaneous with events outside the black hole in this, that some event inside the black hole is simultaneous with some event outside the black hole in this frame of reference. There's no frame that lets you make that kind of comparison. Whereas if you're talking about events outside the black hole, any two events outside the black hole can be viewed as simultaneous in some appropriate frame of reference. But once you're inside the event horizon, there's no frame of reference where you can say those two events happen at the same time. And so it takes away your ability to even think about, really, what's happening to Sally inside the black hole right now? No, Sally is infinitely beyond your future, if you will. Those events simply do not map onto the events of the rest of the universe outside the event horizon. Woo! Right.
So,
Yes.
would there be simultaneous events inside the black hole?
Inside the black hole, yeah, inside the black hole, Sally and Fred can be tossing a tennis ball back and forth to one another. It's all perfectly fine if they just ignore the fact that their bodies are about to be spaghettified. If they're cool with that, they can just enjoy tossing their ball back and forth. It's all cool. Yeah. Okay, so things to think about.
So,
Yes.
I don't even know if these are stupid. I don't even know
Yeah,
if these
go
are
for
stupid
it.
questions or not
I
stupid
may not
questions.
even be have a good answer. Just go for it.
So for the star in the black hole, has the universe essentially ended already?
Yeah, in a sense, yeah. Because all future history
Has it already happened?
has already happened. Yes.
Everything that could ever happen.
Yes. Everything that will ever happen has already happened by the time you cross the black hole's event horizon. Yes.
So then, if the black hole eventually radiates away, when they just continue to not exist once you pass the event horizon, if everything's already happened?
That's a great question. So first of all,
I mean, I'm not.
there's what's called the black hole information paradox, as in, so according to classical kind of black hole, general relativity, it doesn't matter what falls into a black hole. All that matters, a black hole has only three properties: mass, angular momentum, and electric charge are the only three properties it has. And it doesn't have electric charge because if it were positively charged, it would suck in some electrons until it was electrically controlled, or vice versa. So really, it's got mass and angular momentum, and that's all you can see from the outside, and it doesn't matter if your black hole was made of marshmallow cream, or neutron stars, or teddy bears, or whatever. All that you know is its mass and its angular momentum. Well, quantum mechanical considerations, information theory considerations have been used to call that into question. And in particular, with the Hawking radiation, is there some characteristic of it that you could use to figure out what it was that had fallen into the black hole? Does the information get out again somehow? Is it somehow encoded in the Hawking radiation, what actually fell into the black hole? And I don't know the answer to that question. I don't know that anybody knows the answer to that question. I don't even know if I'm correctly stating the question. I'd have to read up on that some more. So I don't know the answer to your question either. On some level, if the answer is that the information is destroyed, well, the stuff that comes out isn't the stuff that went in on some level. I mean, it's the energy and mass or whatever, but in other words, it's not Sally, and it's not Fred. So, and they stop existing, right? As conscious entities, they stop existing long before the black hole evaporates from their perspective. And then, I don't know the answer to the following question. I'd like to find somebody who does this stuff and ask them. So there are scenarios where the universe has a finite future history. There's what's called the Big Rip, where the dark energy increases with time such that the expansion of the universe keeps speeding up and up and up super exponentially, and after a finite amount of time, depending on how the dark energy varies with time, everything comes apart. Everything. The scale factor becomes infinite, and so in a sense the universe becomes infinitely stretched and ceases to be on some level. So that means that the material that was on its way to falling into the black hole, what happens? Does it just go away? So then, does the black hole actually exist? Because if the universe ends before the material gets inside the event horizon, it never got inside the event horizon, right? So then does that mean that if there's a big rip someday, there actually aren't any black holes? In other words, that there's actually nothing inside event horizons because the universe ends before anything does. And I don't know, that's how I would pose it to somebody who studies this, and I don't know what their answer would be. I should make a point of.
I believe it would start with, that's it.
Right. Holy crap! Yeah, the ultimate cliffhanger. So what happens to the unit?
Next time on
Yes,
physics class.
Yeah, apparently one Jimmy Fallon does his thank you marshmallow cream for blah blah blah. Apparently one of his once was thank you cliffhangers.
And then the show.
Yeah. I thought that was pretty good. All right. So anyway, we'll throw in. I'm not going to say everything I just said, but I will throw in that the material of a collapsing star never actually makes it inside the event horizon seen from the outside. Worth adding that to the list. Okay, so now let's ask ourselves, what does a shell observer find for the speed of light? And by a shell observer, we mean somebody who is in some way being held, sitting at some constant radial coordinate. So if we imagine this contraption of spherical shells of clocks that have all been set to run faraway time, a shell observer is one of those clocks. Which maybe it's firing rockets to keep from falling through the event horizon, or it's held by rigid rods if it's not too close. In any case, a shell observer is just essentially somebody who has a constant value of R. What does a shell observer obtain for the speed of light? Somebody who lives in a gas station run by a company in the Netherlands.
Dumping oil into the.
Yes.
I didn't know Shell was a.
Yeah, it's a Dutch company.
That's hilarious.
Yeah. What is a shell observer? Observer at constant R obtained for the speed of light. BP is a, what does BP stand for? Yeah, British Petroleum.
Yeah.
So the shell observer is going to measure radial distance using actual meter sticks, right? Remember that if I look at the R value at this end of the meter stick and the R value at this end of the meter stick, they won't be 1 meter apart because of the curvature of space, right? The R values between shells differ from the actual distance that a meter stick would measure between shells. If I'm going to measure the speed of light, I use meter sticks and properly calibrated clocks. So, whereas if I want to use the coordinate speed of light, I would say, okay, the photon was at this R value at a certain faraway time, and this R value at some other faraway time, and then I would take the change in the R values divided by the change in the faraway times, and I would call that the coordinate speed of light. But if I want to measure the real speed of light, as I would see it, so to speak, I would say, no, how far apart are those two nearby events on the photon's world line measured with an actual meter stick? And what is the difference between the properly calibrated clocks readings, the ones that are keeping local time, not faraway time, on those, for those two different events? And then I would take the actual meter stick distance between them and divide it by the actual time, proper time between them. That's what I would call the, not the proper time. The time is measured by properly calibrated clocks. That's what I would call the speed of the photon. So that's what our shell observer is going to do. The shell observer measures radial distance using actual meter sticks. Maybe a better word is radial displacement. How much the photon moved in the radial direction. Using honest-to-God meter sticks. None of those damn R values stamped on the different shells. Obtaining the proper distance. We'll call that dr for our shell observer, which will be dr measured in Schwarzschild coordinates divided by the square root. 1 minus 2gm over c squared r. Right, we've done the usual dt equals d theta equals d phi equals 0. We want only, what I doesn't have to be dt equals 0. I mean, it's just d theta equals d phi equals 0. We just want the difference in the distance between the 2 points where the photon was. And measures time using properly calibrated clocks. Obtaining dt for our shell observer will be proper time equals Schwarzschild time, dt faraway time, minus times the square root of 1 minus 2gm over c squared r, that piece of the metric. That's not proper time along the photon. That's not proper time for the photon itself, because that's all at 0. We're talking about proper time, meaning time is measured by the local clocks between those events. The ones that are at rest with respect to the shell observer. That's what we mean by dt shell. Clocks at rest with respect to the shell observer, time intervals on those are the local value of the proper time that the observer is measuring. So for our radially traveling photon, theta equals d phi equals 0. ds will be 0 along the photon world line again. So we will say that, actually I don't even have to erase that part. We don't even use that. We don't have, we just, here's dr, here's dr shell, here's dt shell. We're just going to divide them by 1 here. We have dr shell over dt shell for the photon. Is equal to, well, notice when we do this division right here that the two square roots will both be down in the denominator and multiply themselves together. Right? In other words, I'll take this and I'll take this and divide it by dt square root. So down in the bottom I'll have dt square root, and on the top I'll just have dr. So this will be square root is, well, the thing inside the square root, so we'll get 1 minus 2gm over c squared r times dr dt for the photon, because the dr and the dt here are the Schwarzschild coordinate dr and dt. But wait a minute, remember dr dt for the photon was plus or minus c times 1 minus 2gm over c squared r. Right, that's the result we just got before. So in other words, the 1 minus 2gm over c squared r terms cancel, and we get, oh, plus or minus c. In other words, if you use meter sticks and if you use local meter sticks and clocks to measure how fast the photon's going, reassuringly you get the speed of light. So a radial photon has speed c as measured by a shell observer. Where's this plus or minus coming from? We could have put this over here. I don't know what you could have been going into this outwards over there. And in fact, in terms of dr shell and dt shell, the metric is ds squared is equal to c dt shell squared, because dt shell was precisely the dt times the square root thing. So c dt shell squared minus dr shell squared minus r d theta squared minus r sine theta d phi squared. Which looks like the special relativity metric, because in flat space-time, the metric is just c dt squared minus dr squared minus r d theta squared minus r sin theta dt squared. Which looks just like the SR metric, but holds only in a small region since we are fixing the value of r sub shell here. We're looking only at a small region around the fixed value of r sub shell. So a shell observer, because the metric looks just like special relativity in any small little region in terms of the shell coordinates like that, the shell observer is going to measure the speed of light for whatever direction the photon is moving. So locally, if I'm on one of these shells and photons are whizzing by, I always say they're going the speed of light as they go past me, no matter what direction they're going. The curvature of spacetime has not, in fact, changed that. Shell observer obtains c for the speed of light in any direction. And so we can say that no observer ever directly measures a value other than c for the speed of light if they use clocks and meter sticks to measure it. Take our pause.